August 12, 1944, 2:17 a.m., inside Oak Ridge, Tennessee. In a windowless industrial hall, fluorescent lights press down from the ceiling, cold and unforgiving. James, a night shift technician, stands frozen in front of a row of trembling needle gauges. The low hum of transformers fills the air, vibrating through the concrete floor and into his chest like physical pressure. The room is hot and dry. The smell of scorched metal mixes with old sweat. One needle drifts past the red line, just slightly, too small for anyone to shout, too large to ignore. James does not know what the machine actually does. He only knows this: if he shuts it down, the entire cycle collapses. If he lets it run, the coils may overheat. The lights flicker. A brief spark flashes inside a metal conduit. Steel strikes steel with a sharp, knife-like sound. Heat travels through the control lever into his palm. Somewhere in the distance, the alarm has not sounded. Not yet. He counts his breaths. He hears his heartbeat pounding in his ears. And in that moment, James understands something without understanding anything at all. The decision he makes in the next few seconds cannot be undone. What was happening here did not fail because of a lack of technology, and it did not succeed because of a single brilliant invention. Oh, the paradox lies somewhere else. To produce one single component, an entire city had to be built, operating like a living organism where each human being functioned as a cell, unaware of the body it belonged to. The real question was never how to manufacture it, but how to force a massive system to function precisely when most of the people inside it did not understand the final goal. This is not a story about victory. It is not even a story about success. It is the story of solving an impossible problem by dividing ignorance into manageable pieces, accepting waste, deviation, and risk, while trusting that the system, as a whole, would stabilize itself before time ran out. Turn the clock back to early 1943. The war had already spilled beyond battlefields and into laboratories, factories, and rail networks. Intelligence reports made one thing clear: time was not neutral. If one side solved the problem first, the balance would shift permanently. Political pressure condensed into a simple directive. Results were required, and they were required soon. There was no safe option, no retreat, only narrowing windows. Within that context, the project was not allowed to choose the optimal path, only the path that could exist within the time remaining. Doing nothing meant prolonging the war, with losses impossible to measure. Acting meant pouring enormous resources and tens of thousands of people into a process that had never been proven at industrial scale. Every decision was shaped by the clock. Machines had to run before they were fully understood. People had to be mobilized before they could be fully informed. An entire city had to rise before anyone could say with certainty what it was meant to deliver. This was the moment when the system accepted error as a structural necessity. Because under these conditions, inaction was not caution, it was guaranteed failure. The technical problem did not begin with a weapon. It began with a microscopic numerical difference. Two forms of the same element, chemically almost identical, differing only in mass. There was no familiar reaction to separate them, no heating, no precipitation, no shortcut. The only available method was magnetic separation, a technique that had barely existed outside laboratory conditions and had never been operated continuously, let alone at industrial scale. The chosen solution was the Calutron, a machine both precise and fragile. Metal was vaporized, formed into ion beams, and bent through a magnetic field. A deviation so small it was almost theoretical determined whether a particle landed in the correct collection slot. On paper, it worked. In reality, a minor thermal fluctuation, a slight voltage drift, or a single overheated coil could collapse the entire process. To operate thousands of Calutrons simultaneously, an enormous industrial complex had to be built from nothing. Its electrical demand rivaled that of a major city. So much copper was required for electromagnetic coils that national reserves had to be borrowed to keep construction moving. Logistics quickly became a nightmare. Measurement instruments lacked sufficient precision. Components failed far faster than predicted. Magnetic fields interfered with one another across adjacent units. Workers were trained not to understand the process, but simply to keep needle gauges within a narrow band. Engineers patched failures in real time, accepting low efficiency as long as the machines kept running. This was not an optimal design. It was a design that could function immediately, while time continued to run out. Once the system began operating, the greatest challenge was no longer theory, but stability over time. The Calutron was never designed to run continuously, yet the war demanded operation day and night. Magnetic fields drifted, heat accumulated, errors compounded slowly but relentlessly. Materials separated today often had to be fed back into the system tomorrow, forming a low-efficiency loop that could not be avoided. Every marginal improvement consumed more electricity, more metal, and more time. The system turned to human operators in a deeply paradoxical way. Thousands of young women, many with no technical background, were trained to respond to needle movements rather than explanations. They outperformed engineers not because they understood more, but because they did not attempt to interpret the system. They learned to keep the machines within a narrow operational window, guided by instinct, repetition, and discipline. Above them, managers watched production charts climb slowly, unevenly. Decisions had to be made with incomplete data, whether to inject more resources or accept diminishing returns. No one could guarantee that tomorrow would be better than today. At the far end of the chain, pilots and final operators waited for output that was never ideal. The material produced by the entire city never reached perfect purity. It reached only what was barely sufficient. No one had anticipated that maintenance would consume nearly as much time as operation, or that a minor failure in one section could cascade across the entire system. The final solution was not elegance, but acceptance, controlled inefficiency, multiple verification layers, endless repetition, and faith that a system built on compromise would hold together long enough to meet a deadline that could not be moved. In the unnamed city, people were not asked to become heroes. They were asked to be on time, in position, and precise. Night shifts blurred into day shifts under artificial light. Fatigue accumulated until it became routine. Mistakes were not treated as personal failures, but as variables the system had to absorb. Most workers never knew what they were contributing to. They only knew that if a gauge crossed its limit, they would be corrected, and if it stayed there too long, an entire line would shut down. There were individuals who stood out, a shift engineer who recognized a machine's rhythm, a young operator who sensed a deviation before an alarm sounded, but none of them existed outside the system. Individual skill mattered only if the system continued to function. The pressure did not come from immediate danger. It came from endless repetition. The same controls, the same sounds, the same quiet fear that a small error tonight could undo the labor of thousands of others. This was a place where human beings were compressed into functions, not because they lacked value, but because the scale of the task allowed no other form of existence. The cost did not appear in a single moment. It accumulated slowly, steadily, and mostly out of sight. Industrial accidents occurred without ceremony. Thermal burns from overloaded coils, electrical shocks from unfinished systems, exhaustion from shifts with no meaningful concept of rest. Some incidents were documented. Others existed only in the memory of night crews, then vanished into the rhythm of continuous operation. Money was consumed at an unprecedented rate. Vast sums of wartime funding flowed into electricity, metals, buildings, and maintenance for a process that never achieved the efficiency its designers had imagined. Time was spent just as ruthlessly. Every shutdown erased hours or days that could never be recovered. The longest-lasting consequence was silence. Many workers left the city without ever knowing what they had been part of. They carried with them a vague sense that health and youth had been exchanged for an unnamed objective. There is no judgment here, only fact. For the system to keep moving, loss had to be absorbed as a built-in component of its design. In the end, the system produced a result that was just sufficient. Not perfect, not efficient by pure technical standards, but on time. From the city that never appeared on maps, material moved quietly into the next stage of a longer chain, one whose endpoint remained invisible to most of the people who had sustained it. The city completed its role not as a symbol of triumph but as a functional segment in a larger process. When the war ended, many machines shut down almost abruptly. A place that had operated at maximum intensity fell into silence. There were no celebrations on the factory floor, no explanations offered to those who had spent years keeping needle gauges within narrow limits. The result existed, but it did not resemble victory. It resembled a calculation completed just before the deadline, less a finished achievement than a problem solved in time. The story of that secret city did not end with the war, because the problem behind it never truly disappeared. In the modern world, the more advanced technology becomes, the smaller and more fragile its bottlenecks grow. A single chip, a rare material, or one seemingly minor process can determine the stability of an entire global supply chain. The lesson is not found in magnetic fields or specialized machines, but in how systems deliberately accept controlled imperfection in exchange for speed and coordination. Today, nations no longer build hidden cities to separate atomic material, but they quietly construct industrial clusters and closed supply networks where tens of thousands of people see only a narrow slice of the final objective. Time pressure, political competition, and technological rivalry continue to enforce the same logic. Systems act before they fully understand. They deploy before perfection is possible. Success, when it comes, is achieved not by eliminating error, but by managing it at scale. And the cost, financial, human, structural, is still paid in advance, with faith that the outcome will arrive before the deadline does. History is rarely decided by the moment a button is pressed or an explosion occurs. It is decided much earlier, inside nameless factories where people and machines are forced to solve the problems behind the scenes, under pressure of time, at a cost only systems are capable of carrying.